Okay, so today we'll be mostly talking about semiconductor detectors. Okay, last week we talked about semiconductor light sources. Today we'll be talking about semiconductor detectors. So, semiconductor light sources are devices. What does it do? It emits light. That is, if we give some electrical signal to the semiconductor sources, it will emit light. And semiconductor detectors are completely opposite of it. It will detect light. That is, if we incident some light on these detectors, then there will be flow of electrical current, and we'll see that it detects light. Okay. So this is the difference between semiconductor sources and semiconductor detectors. Okay. Okay. So moving on to the very first question. Can you see the question? A yes would be good. Can you see the question? Okay. I will
Yes,
assume
ma'am.
that this is yes. Okay. Thank you. Thanks for your reply, Thomas. Thanks, Sajteen. So Dash is a semiconductor device which converts optical signals into electrical signals. I have already told the answer during the introduction of the class. What's the answer?
Ma'am, photodiode?
Yes. Photodiode will convert the optical signals into electrical signals. Okay. Here I had listed few of the diodes. The Xenodiode works in a reverse bias mode, but it is used mostly as a voltage regulator. Photodiode is a device which converts the light signals into electrical signals. Okay, so that's why it's called a semiconductor detector. LED, that is light emitting diode, it will convert electrical signals into optical signals. Okay, so the two has opposite signs. This would be light detector, and this is an LED. Okay. And tunnel diode is a very special kind of diode. It has a negative resistance because of some phenomena called quantum mechanical tunneling. About this you'll study in much greater details in quantum mechanics. What is quantum mechanical tunneling? And if you'll take any electronics course, then you will study about what is a tunneling diode. Basically it works on that principle. Okay. So moving on to your next question. We have an optical receiver. It's a PIN diode. PIN diode means that generally you have seen a PN junction diode. But here what happens? This is my P region. This is my N region. And in between the two, P and N doped regions will be an intrinsic region. Intrinsic region means it's an intrinsic semiconductor. That is, it's an undoped semiconductor where the number of holes is equal to the number of electrons. Okay, and the conductivity of such intrinsic region is less than doped semiconductors. Okay, so dash has dash intrinsic region or intrinsic semiconductor layer. It separates P and N regions, and the diode is dash bias, which helps them to draw current carriers away from the intrinsic region. What would be the appropriate answer? Okay, wide and reverse. Who answered? Deep Patel. Thank you, Deep Patel. Yeah. So the answer is the semiconductor region, intrinsic region will be a wide one, and as I said that the photodiodes works in a reverse bias mode. Okay, it will be reverse bias. So this you see, this is yeah. So here you see, this is a whole mechanism. This picture over here shows the whole mechanism of a working of a photodiode. That is, in a photodiode, there is an intrinsic layer. This is the intrinsic layer, which is in between the between intrinsic layer. It is in between the P-type and N-type, and this intrinsic layer is exposed to the incident photons, that is light. Okay, Then it operates in a reverse bias mode. As you can see, p-type is connected to negative and n-type is connected to positive. So in the reverse bias mode, what will it will do? It will convert light energy into electrical energies. That is, the current flow. The current flow will be flow of current, or the current flow is mostly because of the minority carrier injection. Okay, because of the minority carriers or the minority current. Okay, and this flows through the device only when reverse bias is applied. Okay, so I hope that when we you understand that when we are increasing the light, okay, when the incident light increases, then more and more of current will flow in this. As you can see from this diagram, it's quite visible, and obviously, and can you tell me which will be the direction of the current flow? Will it be from this side to this side or this side to this side? N to P or P to N? What will be the direction of the current flow? This is a very simple question. Very simple. Will it be from N to P or N to P to N? So the current flow is because of the minority carriers. There is light is incident over here. There is electron hole production. That is, electrons and holes will be produced, and they will move away from the depletion from this junction. Electrons will be pulled on this side because it's positively charged. It's connected to the positive terminal of the battery. These are the electrons. It will be pulled this side, and the holes will be pulled on the either side. Okay, so you can see from the diagram, it's quite visible from the diagram. So can you tell me about the current flow?
P2N.
Current is flowing because of the minority carriers, and it is reverse bias. In a forward bias, how is the current flow? So we have a forward bias, okay, positive to positive, negative to negative. So what is the current flow? Forward bias mein, it's because of the majority carriers mostly. So this is the current flow, right, from P to N in a forward bias diode. So what will be the current flow in a reverse bias diode where more N to P, correct. It will be from N to P, from here to here. Try to think about this. Okay, try to have an intuition, get a feel and intuition of this, that why is it N to P. Try to correlate it with the forward bias. In the forward bias, where the width of the depletion region keeps on decreasing and decreasing. So this is connected to the positive terminal, this is positive, the negative is connected to the negative. Okay, so more of holes will be repelled this side and more of electrons will be repelled this side, and so there will be a flow of current from positive to negative, that is from P to N. But here it is happening, what is happening? The opposite thing is happening. More and more minority carriers are being generated. Current flow is because of the minority carriers. Okay, so it will be from N to P. Okay, just think about it. Think about it once and let me know if you have any more confusions regarding this. Okay, get a feel for it. Try to have an intuition for that, how the whole mechanism is going. Like here it has been shown. Okay, now I'm moving on to the next question. The responsivity of a package PIN photodiode can be controlled by changing a semiconductor material use, the wavelength of the incident light, photoelectron conversion efficiency, or incident power. What do you think would be the answer to this question? I'll give you a second to answer this. C. Photoelectron conversion efficiency. Okay, Deep Patel says C. Any other answers to this? Any other answers? B. Wavelength of the... Okay, Deep Patel first says C, now B. Okay. Okay, anything else? So, before moving on, I would like to ask you, what do you mean by responsivity? Okay. What do you mean by responsivity? What do you mean by that? So, basically, Okay, yeah, it's writing. Responsivity, right? Is that the correct spelling? Responsivity. Yeah, it is defined as the ratio of the photocurrent that is produced by the whatever is the intensity of the optical power. Okay, optical power, whatever is the optical power of the incident light, whatever is the optical power of the incident light. That is how you define responsivity. So now where the wavelength and photon efficiency is coming over here, this is the definition that like how much is the conversion of the optical power to the electrical current. Basically it's asking about that. It tells us about that, how my diode is responding, what is the response to the optical power. The response is the photocurrent. So what is the response of the my device to the optical power, to the opticals? So how is wavelength or efficiency coming over here? How it gets related to that? Any answers? So I'll tell you. See, if you have a photodiode over here, okay, light is incident on it. Say one photon, only one photon of energy, h nu, is incident on it. Okay, so let's say that every photon, okay, so this h nu will generate one pair of carrier. Let's say this every single photon is generating few carriers, and that few carriers, how many electrons per second it is generating. Okay, so it will produce some photon flux. One photon produces photon flux. Okay, sorry, photon flux I'm saying, it should be electron flux, I'm sorry. So it is so this one photon is producing some electron flux, some electrons, few electrons per second. Okay, so every photon is producing that electron flux, say phi, and so how much will be my photocurrent? Okay, photocurrent or IP will be equal to E times the photon flux, electron flux. Here phi is the electron flux, that is number of electrons per second. Okay, so if the number of electrons per second is phi, that is electron flux, so how much current will be produced? That times the electronic charge. Okay, that much photocurrent will be produced per photon. Okay, so so now what are we supposed to do? So now my this optical power is said to be optical power. What is optical power? Say optical power P is equal to h nu phi. Say here phi, I'm saying that number of photons per unit time, and that number of photons is producing some electron flux. Let that be equal to also phi. Okay, so now what will be my photocurrent? So my photocurrent will be equivalent to what? Let's substitute this phi over here. This will be phi is equal to P by h nu. So that will be equivalent to IPH is equivalent to E times P divided by h nu. Okay, so this is my the photocurrent. But there is some term which is called the quantum efficiency. Now what is known by quantum efficiency? That is how much of light energy is converted into electrical energy, how much light is getting converted into the photocurrent. Okay, that is known as the quantum efficiency. So basically quantum efficiency is the rate of electron generation. Okay, quantum efficiency is the rate of electron generation divided by the rate of photon incidence. Rate of incident of photon. Say photon incidence. Photon incident on the device. Incident on the device. On photodiode. So this is my efficiency. So this has to be multiplied with that efficiency, because each photon may not produce an electron hole pair and each photon may not result in the production of photocurrent. There might be some efficiency associated with it. Suppose 60% of light gets converted into electrical energy, or 70% light gets converted into electrical energy. That's how you define efficiency. How much input, how much output we are getting for my 100% input. Okay. So, my photocurrent would be this quantum efficiency times the electronic charge times the whatever the power we are incident time, divided by h nu. Okay. So now what? Now I see that my photocurrent produced is proportional to the incident power. So now this proportionality constant, there is this proportionality constant. That proportionality constant is known as the responsivity. That proportionality constant is known as the responsivity. Okay, and that we can write in terms of the wavelength Ne by Hc times lambda, or if we convert E by Hc, that will be 1.24. So this will be eta lambda by 1.24, right? Wait, will this be eta lambda by 1.24?
Yes.
Yes, ma'am.
Yes. So this will be eta lambda by 1.24. Okay, and that will be in micrometers. So we see my responsivity is dependent on lambda, but there is a factor eta. Eta is my quantum efficiency. Okay, but now what is quantum? So we should know what is this quantum efficiency dependent on. Okay, what is quantum efficiency dependent on? Can anyone tell me? So I'll tell you what is this quantum efficiency dependent on. It will be depending on my absorption coefficient. Okay, is this the right spelling? Depending? No, sorry. This quantum efficiency will be dependent on the absorption coefficient. Dependent on absorption coefficient alpha. Okay, that is how much light is getting absorbed by my device. Okay, so that is alpha. But again, what wavelength will get absorbed, that is also dependent, right? Whether my device will absorb that much wavelength or not. So this absorption coefficient is again dependent on the wavelength of the incident light. Okay, again it depends on the wavelength of the incident light. So there is some cutoff wavelength associated with every device, every semiconductor, and so this absorption coefficient should also be dependent on the wavelength of the incident light. Hence my R will be depending on the wavelength of the incident light. So you got this point? Absorption will not be occurring if the wavelength is greater than some cutoff wavelength, because then because these these are all semiconductor devices, and these semiconductor devices has certain band gap. So the wavelength of the light incident should have energy, should correspond to energy which should be greater than or equivalent to the band gap of that semiconductor material used. If the band gap, the energy of the incident light is less than the band gap energy of the semiconductor material, then that will not be absorbed and my photodetector will not be detecting any signal. Okay, no photon will be getting converted into photocurrent. Okay, is it clear? I hope it's clear. So now let us move on to the next question. Okay, the most appropriate way for reducing the response time of a PIN diode is by changing applied reverse bias or cross-sectional area, both A and B, or it cannot be reduced. So before that, can you please tell me what is the meaning of the response time? What is response time? Please answer. Deep Patel, can you please answer? What is response time?
The time taken by carriers to generate the current.
Yes, sir. So,
Because that is needed to detect the light. Depletion layer is increased, so more amount of light gets absorbed. one one more layer is added in PN junction diode. Because a phenomena called impact ionization occurs here. Uh, the carrier combination increases. Alpha H by alpha E. Yes,
Now visible one.
Okay, so my answer is B. So now let's move on to our next question. Next question is, my avalanche photodiode has a quantum efficiency. My eta is given 50%. Wavelength is 500 nanometers at zero bias voltage. If the device is operated with a reverse bias such that it provides a multiplication factor and M is equal to 8. M is given. So how are you find the responsivity at that bias voltage for this APD? So for that, we know that responsivity of APD is equal to M times the responsivity of the PIN photodiode. Okay, so I have to find the responsivity of the PIN photodiode. That's simple. We did the derivation in the last question. That is eta times lambda by 1.24 micrometers. Just find out and just multiply this by 8. That is, RAPD is equal to 8 times eta lambda by 1.24 micrometers. Yeah, lambda is in micrometers. Just change lambda to micrometers. Okay, so or here they have done directly and they have not changed it. So it has been done directly. It has not been changed, like that 1.24 factor has not been taken into account over here. But this is also right. It's basically converting this Q by HC to 1.24. Okay, and lambda would be in micrometers. Okay, so just check on these values whether this is correct or not and let me know. Okay, I've done the calculations. I think it is correct. Okay, now let's move on to the next question. Here there is a group 1. It lists quite a number of diodes, and group 2 lists the bias associated with these devices, either forward bias or reverse bias. So tell me, is diode forward bias or reverse bias?
Reverse.
Yes, diode reverse bias. Therefore, P goes to 2. Solar cell, forward bias or reverse bias?
Reverse.
No. Solar cell will act in a forward biasing. It will produce current, but it is in forward biasing. So Q goes to 1. You read about solar cells, you'll get an understanding of it, because a good solar cell will be a bad photodetector, and a good photodetector is a bad solar cell. Just get an idea about that. Okay, it will be acting in a forward bias. Laser diode, forward bias or reverse bias? We have done it. It's completely
Forward.
yeah, forward bias. Avalanche photodiode.
Reverse.
It's reverse. So P2 Q1. Next question, next statement is, the photocurrent of a reverse bias photodiode under illumination varies exponentially with light intensity. And then the next is, the spectral response of a photodiode does not depend upon the frequency of the incident light. Okay, which of these statements are correct? We'll go one by one. The first statement says, okay, I have not given a slide for here. The first statement, radiation falling on a photodiode is primarily a minority carrier injection. So what is happening in a photodiode? As we have done a number of times, in a photodiode, touching and changing the slides. Okay, in a photodiode, what is happening? A photon falls, photon will fall. Photon fall will produce, generate carriers, okay, So basically this will drift from the junction, that is intrinsic layer, towards the terminals of the battery, okay. So this will generate currents, okay, generate a large amount of carriers. That is, the electrons will move from p side to n side, and the holes will move from n side to p side, okay. So basically the whole current is because of this minority carrier injection, Okay. So basically this whole current is because of this minority carrier injection. So what will happen? My conductivity, that is more and more current will be generated, and so the conductivity will increase. So there will be this minority carrier injector. The radiation falling on the photodiode is a minority carrier injector. So this is correct. Okay. So one is correct. Let's look at the second statement. That is, the photocurrent of a reverse bias photodiode under illumination varies exponentially with light intensity or not. So let's see about the photocurrent. We have already done about this, right, in the responsivity. So this photocurrent is basically eta E by hc times lambda times whatever is the optical power. Okay, hc by lambda is basically what? The photon energy, right? hc by lambda is the photon energy. So this photocurrent IPH, here I'll write hc by lambda is the photon energy, and eta, as I say, is in efficiency. So in no way we can see that this photocurrent is varying exponentially with the intensity. So this statement is incorrect. Now let's move on to the next statement. Spectral response of a photodiode does not depend on the frequency of the incident light. Do you agree to it or not? Please tell me. Spectral response, that is the range of the optical wavelength. Okay, range of wavelength, range of lambda or nu. Okay, so does the photodiode response to it, does the response of the photodiode depend on the frequency or of this light? Yes, it will depend, because these photodiodes have certain band gap, and the incident light should have an energy which should be greater than this band gap or equal to the band gap. And so this energy is dependent on the frequency. The energy is equal to h nu, right? So it will depend on the frequency and not on the intensity of the incident light. Okay, it is lambda dependent or nu dependent. So basically it's determined by the material that we are using. So only one is correct. Now let us move on to the next question. Again, we have an avalanche photodiode. The gain M is 20. It is operating at such a wavelength, and I know the responsivity. So you need to calculate the quantum efficiency. Can you do this? We have done a similar type of question previously. Let's see how this is done. So, as I said, RAPD is equal to MRPIN, and that will be M times eta. Let's take E by H nu times, HC times lambda. Right? Am I missing out anything? No. So from here you can find the eta. Eta will be equal to RAPD times HC by M. Am I doing it something wrong? And by M E lambda. Yeah. This will be this is how you'll find the quantum efficiency. Just substitute the values and find out. We know all the values given over there. Okay. Wavelength is given. R is given. M is also given. Okay. That is all you need. H and C are universal constant. C is also a universal constant. The quantum efficiency, eta, is it wavelength dependent? Because of the absorption coefficient is wavelength dependent. Is this question true or false? Is this statement true or false? Is it true or false?
False.
Quantum efficiency is, just a second please. Someone's running? Yeah. Quantum efficiency is wavelength dependent. Why quantum efficiency is wavelength dependent? We did it just a while ago, right? Will the absorption coefficient depend on the wavelength or not? Yeah, that is true. The absorption coefficient. As I told, no, why is absorption coefficient wavelength dependent? Can someone tell me? Will my diode absorb whatever wavelength I am giving? No, that has to be less than the cutoff wavelength. Right? Absorption, I'll just write it over here. Absorption cannot occur when lambda, say the cutoff wavelength. So whatever lambda is incident. Lambda incident, I'm sorry, I shouldn't write it here. Okay. When lambda incident is greater than some lambda cutoff. Okay, and why? Because this lambda cutoff is just same as the energy band gap. Lambda cutoff, that is hc by lambda. Because of this reason, sorry, since the energy band gap is equivalent to hc by lambda cutoff. Okay, if the wavelength is greater than this, then the energy of this will be less. Okay, if lambda incident, uh, just a second. Huh. Yeah, so if a lambda incident is greater than lambda cutoff, then what will happen? This will imply that the energy of the incident wavelength is less than the energy of the band gap, e.g. then this will not be absorbed, right? This will not be able to generate the carriers. So my quantum efficiency is wavelength dependent because the absorption coefficient is wavelength dependent. So this statement is a true statement. Am I clear, Deep?
Yes.
Yes. Okay. So any other questions? We come to the end of the class. Any doubts? Any questions?